Hello, young people. Ms. Rains. I am here to talk to you a little bit more about types of chemical reactions. We're going to try to go through this quickly, so hopefully you can rewind, okay? Chemical reactions versus chemical equations. Basically, a chemical equation is the sentence that describes a chemical reaction to us. So as chemists, the chemical equation is our sentence. The chemical reaction is the statement of what's changing. They both represent similar things. Chemical reactions tell us the changes. Chemical equations are the sentence that we write down for that change. Okay, a chemical reaction is basically a description of the transformation of elements and compounds into new substances. So elements and compounds combine together, they shuffle out, and they form something new, and that is called a chemical reaction when that happens. We have balanced chemical equations that show the relative amounts of reactants and products. So we know that we have the relative amounts. We'll talk a little bit more about balancing in a minute. Phase symbols, we have 4 phase symbols, an S, an L, a G, and an AQ. Those phase symbols are really important to us because they're trying to identify what we know is happening chemically. S stands for solid, L stands for liquid, G stands for gas, and AQ stands for aqueous solution. Those are really important for us to include, especially when we're talking about precipitate reactions and other reactions where we're trying to figure out the driving force and figure out what's really going on and whether or not they happen. Energy and time are never alluded to in a chemical equation or necessarily in a chemical reaction. We're just talking about the change. Energy and time come into play a little bit later on, and we'll be talking all about energy and time. In kinetics, we'll be talking about time, and in thermodynamics, we'll be talking about the energy changes that are associated, because we know there's energy, we know it takes time, it's just not mentioned in the chemical equation. We have to add that a little bit later. Antoine Lavoisier was the first guy who came up with this idea of the law of conservation of matter. And it's one of the reasons why we have to balance equations, because what he figured out is when he started with certain amounts of stuff, he ended with certain amounts of stuff. And it was always the same. Nothing changed about what he started with. So even though he didn't know there were atoms out there and he didn't quite understand how everything was put together, he could figure out in closed systems that when he started with stuff, and he did a chemical reaction and he looked at it and it was different stuff, it still had the same mass. So that was really important, even though we hadn't yet come up with the idea of an atom just yet. That's why you balance equations. So if you want to blame anybody for balancing equations, blame Lavoisier. Okay, the first kind of reaction we want to talk about is synthesis. 2 or more simpler substances combine to form one more complex substance. Basically, A plus B yields AB. Identifying it is pretty simple because our product is only going to be a single product. We're going to have one thing, and that is usually a combustion reaction or a combination reaction or synthesis reaction. Those can also be combustion reactions. If we have metals that are burning, we're going to get a synthesis reaction with that as well. So, combination of magnesium and nitrogen to yield magnesium nitride. So here we have the magnesium right here, the little purple spheres, larger. Nitrogen a little bit smaller in the blue spheres. Notice nitrogen is together because it's a diatomic molecule, Brinkelhoff, remember? And then we form this magnesium nitride, this substance that has 2 magnesiums to 3 nitrogens. Now this is a little hard to show, but it's there. Another combination reaction is the combination of hydrogen gas and oxygen gas to produce, water, hair. There you go. We know that very well. So what happens is we have hydrogen here and water here, and it forms, or hydrogen and oxygen, sorry, and it forms water. But notice there's a proportionality, and this is where Lavoisier began thinking about it. You know, he could take things, he could combine them together in closed containers, and when he got the same mass, he was like, oh, hang on, there has to be something going on. And then much further down the road, we began to figure out there are particles and what those particles were called and how to put them together. So as we get more and more sophisticated, we understand more and more about chemical reactions. Decomposition reaction, obviously the opposite of a synthesis. Decomposition is breaking down, synthesis is building up. So we take a more complex substance and we break it down into its simple parts. So AB goes to A plus B. A and B are not always elements. Sometimes they're the elemental form, sometimes they're just simple compounds. So a single reactant breaks down into 2 or more products. That's basically one reactant. Like synthesis, one product, this is one reactant. Hydrogen peroxide decomposes into water and oxygen gas. Hydrogen peroxide is really similar to water. If you look at its formula right here, it's 1 oxygen away from water. And you're like, well, why doesn't it just form hydrogen and oxygen? It just doesn't. It doesn't naturally do that. Water is very, 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 it's a very good molecule. And water holds together really well. So given the opportunity, if you have enough oxygen, you'll form water before you'll form oxygen. It's just in a water molecule, breaking it apart wouldn't quite happen like that. Now, hydrogen peroxide breaks down naturally on its own, actually, in the environment. It's one of the reasons why we buy it in a brown bottle, because sunlight actually makes peroxide decompose more quickly. This actually occurs naturally in your body, which is why we have the enzyme catalase in our body to get rid of any hydrogen peroxide that might be there. It's automatically in our blood. As a matter of fact, as soon as you add peroxide to any open cut or wound, what does it do? It bubbles. The bubbling means it's breaking it down, forming water, and the bubbles are oxygen gas. There you go. All right, trying a little thing out here. So combustion reactions. Combustion reactions is any combustible material in an oxidizer can combust. The most famous of oxidizers is oxygen. We're going to talk more about oxidation reduction a little bit later, so don't panic here because I'm going to go through this really quickly. We've kind of told you that the only combustion reactions are hydrocarbons, and that's not really true. They're really a subclass of combustion reactions. So it's truly incorrect to say that these are the only combustion reactions. So unfortunately, I taught you something that was not completely correct, but I did it for a very good reason. I was trying to give you a way to recognize. So magnesium ribbon burning in oxygen does not produce carbon dioxide water because there's no carbon or hydrogen available to make carbon dioxide or water. Instead, it makes magnesium oxide. We've seen this happen. But this is truly combustion. We would classify it as synthesis because we were trying to make things simple, but it could also be classified as combustion reaction. Cellular respiration, on the other hand, is the most classic form of combustion reaction of all time. It happens in our bodies all the time, all the time. So here we are. We have the glucose here, the glucose here and the oxygen, and we say that it creates carbon dioxide, water, and energy. And that's all the end products. And you know what? It's all fancy because in chemistry we just want the beginning and we want the end. And we don't always worry about the chemical equation, doesn't worry about the middle, but we know the middle is vast here. It's a very vast situation. So we've got to be understanding of that. But there's our ATP created. Single replacement reactions, simply a single uncombined element replaces another element within a compound. I say elemental too because I'm trying to distinguish between those diatomic molecules and atoms and making sure you understand that it can be elemental as well. That diatomic molecule can do the same thing. And we get A plus BC yields AC plus B, and we can see it switches out and somebody else becomes single instead. Zinc metal with hydrochloric acid yields zinc chloride and hydrogen gas. In this case, the zinc was all by its lonesome self. It added to hydrochloric acid. We get zinc combined with chlorine, and hydrogen goes off by itself. Notice this little symbol right here. It's just another way to signify gas is being produced. Also notice we need two hydrogens to balance out the equation because we have two chlorines because of the zinc, and H2, of course, is always like that. So there's the reaction with zinc chloride. Double replacement reaction, and this is kind of where we are. We understand this first part. Anions and cations of two ionic compounds switch places to form brand new compounds. We get that. We get AB plus CD yields AD plus CD. You guys can do that. I know you can. I've seen it. This is where we go wrong. Lead nitrate reacts with potassium iodide to form lead iodide and potassium nitrate. How can we predict that? You're saying, oh, it happens. Well, the prediction comes because we form a solid here. Why do we form a solid here? Well, let's see. We have lead and we have iodine. Chlorides, halides, coals, the NaCl-NoSo, the coals, say that PMS are insoluble. That's lead, mercury, and silver. This is a lead iodide, so it's insoluble. We take two clear colorless solutions, we put them together, and we get this bright yellow substance. We've seen that before. So this is where we're at right now with precipitation reactions. It's just a fancy way to say double replacement. Acid-base is a fancy way to say double replacement. So we want to see what that looks like on the atomic level, on the nanoscopic level that we can't actually see, but we need to be able to understand. So what happens is you have a, I'm trying to find my, you have a beaker full of the aqueous solution, and we see all the little different species. We've got the potassium, we've got the barium, we've got the nitrate with the little green, we've got the chromate with the little yellow in the center. And what's happening is these are all bouncing around and moving around in this beaker. Well, the problem is when a chromate finds a barium ion, what happens is they stick together, and when they stick together, they go, hey, I really like this. and they form a solid and they precipitate out. So you'll see in this beaker now the barium and the chromate are now stuck together just like over here. They form this yellow precipitate. Notice what happens to everything else. Everything else is still in solution. Looks exactly the same as it did before. So the potassium and the nitrate are considered spectator ions. The barium and the chromate are not spectators because they've formed the solid. Okay, so when a precipitate is formed, it's considered a driving force for the chemical reaction. That just means that it's favorable. The chemical reaction will occur because this is going to happen. We're going to talk about this a little bit more in thermodynamics, but just understand, driving force means that a chemical reaction is going to happen. If I see it, it's the driving force that's making the chemical reaction occur. A precipitate is an insoluble solid that forms when two aqueous solutions are mixed together. So I take two solutions that we can't see anything in, mix them together, and boom, just like the bright yellow, I get something that wasn't there before. We are going to be doing this lab starting on Friday. It's going to take several days, but we're going to start it on Friday. We separate the precipitate from a solution by a filtration process called gravimetric analysis. And this is going to be where we separate it, we dry it out, we measure it, and we figure it all out. So we will be doing that as we go along there. So to know if a precipitate forms, you have to know your solubility rules. So here they are. NaCl-NoSo. Remember, Na stands for the alkali metals and the ammonium group. The Col stands for the halides, minus fluorine. Fluorine's a weird halide, so we're not going to worry about it too much, but PMSs of any halides are not soluble. That's lead, mercury, and silver. Nos, nitrates. All nitrates are soluble. All. If it's a nitrate, it's soluble, for sure. SOs. SOs can stand for a lot of things, but SOs mean that there are some things that are soluble and some things that aren't. For the most part, they're soluble except for PMS, that's lead, mercury, and silver, and what I call potassium, calcium, barium, and strontium, okay? Now, we come over here, and I jacked it up because I still have stuff over here. So equation 1 over here does not actually occur. Equation 1 doesn't actually occur because everything is going to be soluble. Barium combines with nitrate and it's soluble. Potassium combines with chloride and it's soluble. According to all the rules, it's soluble. We go to letter B and we see that when lead combines with sulfate, that's not so good because it's a PMS. PMS means that the lead and the sulfate are going to precipitate out. So we're going to get lead sulfate as a solid, okay? We go to C and we see we have potassium hydroxide and iron nitrate. So we switch those and we know, okay, we're going to get iron hydroxide and potassium nitrate. Well, let's think about that. Potassium and nitrate are both soluble, so that's going to be an aqueous solution. Let's check the other one. Iron and hydroxide. Now, this isn't covered in your NaCl-NoSo rules. So if you looked up hydroxide, you would find out that iron 3 hydroxide is insoluble. And so that reaction will occur. So B and C will occur, but A will not. All right, so describing chemical reactions or aqueous solutions in chemical reactions. We have 3 ways to do it. The complete balanced equation. You can see what all that is. We also call this the molecular equation. Then we have the complete ionic equation. That means we've taken everything and we've broken it down and made it look like what it looks like in the beaker. But that's still not the true picture of what's happening in that reaction, and we want a true picture. So we end up with the net ionic equation, and this is most like what's happening in the container, most like what matters what's happening in the container. So it only includes the parts that are reacting. Anything else that's not reacting is considered a spectator, and we don't write it down. So in the beaker that we saw before, potassium and nitrate were spectators. We don't write that down. We always make sure we conserve charge and mass when we're talking about these. So the first reaction we have potassium chloride and aqueous silver nitrate to form silver chloride and precipitate. This is a precipitate plus aqueous potassium nitrate. So the molecular equation, there it is. It's already balanced. Complete ionic equation. Everything's been broken down into its ions except for the silver. The silver right here hasn't been broken down. Okay, then we go to the net ionic. The net ionic, it only includes the important pieces. So anything like the potassium that hasn't changed on either side and the iodine that hasn't changed on, or no, I'm sorry, not the iodine. Okay, so the potassium and the nitrate that hasn't changed on either side are gone away, leaving us with silver and iodine and that other one. That's all that we're going to have time for, so I'm going to stop it right there, and we'll be back with another thing a little later.